In this example, we're going to integrate using trig substitution. Now, this is the second video in my series for trigonometric substitution to evaluate integrals. The first video really talks about where we get these formulas from that I'm going to be using. And what we discussed in our first video was depending on which one of these three formats we had, that would allow us to determine how to choose our trig substitution. And in this case, because I have a constant squared plus a variable squared, constant squared plus variable squared, I'm going to use tangent. So I look at the denominator here. I know I'm going to use my tangent version. And that's because I have a squared plus x squared, which really that's the same as 4 plus x squared. And you want to note that 4 is actually 2 squared plus x squared. So you should see here that my a value, a is not 4, a is equal to 2. So in order for us to create this substitution, we set x equal to 2 tangent theta. Obviously, if we were to differentiate that, the derivative of x with respect to theta would be 2, and the derivative of tangent is secant squared theta. So multiplying by d theta on both sides, I can say that dx is 2 secant squared d theta. Now, keep in mind we have a inverse range restriction for tangent inverse, and that theta must be, and this would be not inclusive, an open interval between negative pi over 2 and pi over 2. And if we think about drawing our reference triangle here, I always try to draw them the same way, and I put my reference angle in the lower left corner. Theta, well, remember we said we would identify this and say tangent theta equals x over a. Now remember, tangent is opposite over adjacent, so this is x as my opposite side and 2 as my adjacent side, and my hypotenuse would be 2 squared, or 4, plus x squared. So just to recap what I'm doing here, I looked at my pattern. I said I'm going to use tangent, and I know that tangent is going to come in this form, a squared plus x squared under the radical. This lets me know it's tangent. And I identify then that my a value is 2. So if tangent theta is x over 2, then that means x is going to equal 2 tangent theta. Differentiating x, we're going to get that dx is equal to 2 secant squared theta, d theta. We have one more step we need to deal with, and that's kind of the way we think about what this is going to turn into once I substitute that x value in here, right? Because x is going to be 2 tangent theta, dx is going to be this 2 secant squared theta, d theta. But instead of doing that in the problem, I like to do that first. So if I think about 4 plus x squared, what's that going to be? That would be 4 plus 2 tangent theta squared, or 4 plus 4 tangent squared theta. If I factor out that 4, that would be equal to 4 times 1 plus tangent squared theta. And 1 plus tangent squared theta is secant squared theta by the Pythagorean identity for tangent. 1 plus tangent squared theta equals secant squared theta. So at this point, I'm going to scroll and kind of use what we have here on our screen. We start with the integral of dx over the square root of 4 plus x squared. So I have a dx written, and I've also identified what 4 plus x squared would equal. So I can rewrite this. This is the integral of 2 secant squared theta d theta divided by the square root of 4 secant squared theta. So I did a lot of front work here with my basic trig substitution. And if you know the formulas that go along with the pattern, that's going to make this a lot easier. Of course, if you don't know the formulas, you can derive all of this as we just did. I knew that this pattern led me to use tangent. Tangent is this pattern, so my A value is 2. And of course, that pattern then, tangent theta is x over A, gives us x equals 2 tangent theta, and we can differentiate it, and we can also figure out what that substitution is going to look like. So I'm going to scroll back down, and let's finish working this problem. So I've got the integral for 2 secant squared theta d theta, and the square root of 4 secant squared theta is 2 absolute value of secant theta. Now, because we know that secant theta is going to be positive, we are specifying that theta is between negative pi over 2 and pi over 2. That means secant theta will be positive, and we can drop those bars. So I can just say, well, this is 2 over secant theta. And you'll notice that the 2's cancel, the squared secant in the numerator cancels, and this is now the integral of secant theta d theta. Now, looking at our table, we know an integral for secant theta. This is not secant squared. The integral for secant squared is tangent. So looking at the integral table in our book, if we look at number 95 in the table, we know that the integral of secant theta d theta equals the natural log of the absolute value of secant theta plus tangent theta. Running out of space. So the integration of this becomes natural log of the absolute value of secant theta plus tangent theta plus c. And of course, we didn't start with theta. We started with x values, right? So we need to go back into that format. And what we want to remember, we said that tangent theta is x over 2. We had this reference triangle, which looked like this, theta, x2, and then we've got the square root of 4 plus x squared. So this was our reference triangle that we started with. What is secant in terms of that triangle? Secant theta, remember that secant is the reciprocal of cosine. Cosine's adjacent over hypotenuse, so this would be hypotenuse 4 plus x squared over adjacent 2, and then tangent theta is given. So if we convert back, this becomes the natural log of secant theta, which is the square root of 4 plus x squared over 2, plus tangent theta, which is x over 2 plus c. And that's our final answer here. As always, please email me if you have any questions. I'm going to do, I think, 2 more examples in this section. So there'll be 2 videos following this. One with secant substitution and one with a sine substitution.